Hello everyone. Let's move forward with our chapter Light. Today we shall be taking the topics from reflection. In reflection, we shall be taking the cases of plane mirror and spherical mirrors. In between, we shall be discussing also about the object and image. Alright. Let's take it one by one. Just like what we have discussed earlier, reflection is a phenomena in which a light ray, when hit on a surface boundary, goes back in the same medium. Reflection, that boundary or that surface on which our light ray is hitting, it is our surface. And in all the cases that we shall be taking forward would be the cases for regular reflection, that is regular surfaces, and any highly polished regular surface is called a mirror. Now, talking about mirrors, depending on their shapes, mirrors are of two types. First one, a straight mirror called as plane mirror. Second one, a mirror whose surface is curved. It is known as spherical mirror. Let's take the case of plane mirror first. How our image is formed in plane mirror. But before switching on to plane mirror, we must know the concept of object and image. Let's move on to our first concept. Object and image. Have you ever considered the case when you are viewing your own reflection in a plane mirror? For the plane mirror, you are the object and the reflection you are viewing inside, that is the image for plane mirror. But for your eyes, which one would be the object? Of course, it is not you. The object for your eyes will be the reflection in the plane mirror, and the image so formed will be in your retina that senses your brain. So, object and image, basically, these two are your relative terms. For different objects, they could be switched. Alright, now, what about the object? Object could be any source which is emitting out light. That source could be a real source, or what we say a real object. That source could be a virtual source, or what we say a virtual object. What about a real object? This source is giving out or emitting out light on its own, that is, light actually diverges from it. What about our virtual source? Here, the light appears to converge at it. So, our sun or lamp or table or chair or even a human being, they all are real objects. Virtual objects could be the objects such as our reflection in a plane mirror or reflection in a convex mirror. These all are called as virtual objects where light rays appear to be coming from that point. Light rays appear to converge at that point. Coming on to our image part, just like the object, if the light rays are actually intersecting at a point, that image will be called as real image. And if our light rays appear to diverge from a point, that would be called as virtual image. Here, whatever we have done actually in the case of real, in case of real image, that would become just opposite. In virtual, whatever be the case of appearing in the object, that case would become opposite in case of virtual. That is, light appear to diverge from it. Alright, talking about our real images. Real images such as in the case of concave mirrors, if we are talking about reflection, or such as in case of a convex lens when we talk about refraction. These real images would be taken on a screen. A screen could be anything, any thermocol sheet or any A4 size paper or any board surface, such as your projector or whenever you go to PVR or movie theaters. The images or the movie that you see on the screen, that is the real image. It cannot be taken on a screen. Now, real image with respect to its just object or immediate object, it is always inverted. Whereas virtual image with respect to its immediate object, it is always erect. We learn it using the acronym RIVER. RIVER. Real image with respect to its immediate object will be inverted. Virtual image with respect to its immediate object will be erect. This is what we need to learn. Now, whether the object is real or virtual, whether the image is real or virtual, let us take one example, a case from a plane mirror. Let me raise it first. Consider the case of image formation by a plane mirror. This is our real object, let's say AB. Its image is being formed behind the mirror. This is our mirror, let's say M dash. The image of this object, let's say AB object, is formed behind the mirror as A dash, B dash. Now, if you could just observe for our plane mirror, this object as a real object, this image acts as a virtual image. But for our eyes are viewing the image directly, right? So this image would act as a virtual object for the eye. Remember this thing. And the image that is formed behind the retina inside our eye, that will be a real image for this virtual object. That means same object or same body could be object or image for one substance and it could be an object for the another one. Hence, I said that object and image are relative terms. Okay? Now, if you are just observing here, any two rays are required to form an image of a point. Since this is an extended object would be taken as a collection of our point objects. If we just look this object and we just move from here to here across its boundary, we would see that this object is a collection of too many point objects, right? The image formed of this object or in this mirror will be exactly at the same distance as the object is. This distance will be same for both. So, for the characteristic of the image formed in a plane mirror, the characteristic would go like number 1. The image is, of course, if object is erect, image is also erect, and we have already studied that virtual image formed will be erect with respect to object. So here, in case of plane mirror, the image formed is virtual and erect. The image formed is exactly as the same size that the object is. So basically, our image is same size as our object. Number 3rd point, it is equidistant from the mirror. The object is some distance in front of the mirror, exactly the same distance our image would be behind it. So our image is equidistant from mirror as object is. Alright. Number 4th point. If you could just observe this point C. The point C, which is near to the mirror, has its image near to the mirror, right? That means our image has did nothing, but it is being shifted laterally. It has been inverted laterally, not upside down. This kind of inversion is known as lateral inversion. Alright. These are the 4 characteristics of the image formed in our plane mirror. Now, let's come on to our part where we will see reflection through spherical mirror. Right. Suppose we have got any glass sphere. Somewhat of this shape, and we just take this part and this part of our glass sphere, right? Such that for this part and for this part, I am polishing here the outer surface or bulging out surface. Here I am polishing the inner surface. Alright. The part there that you are looking over here, where our reflecting surface is the concave part or the inside part, this part. This is known as our concave mirror. Here, where the reflecting part is our bulging out part, this part, or the convex part. So this kind of mirror will be called as convex mirror. Now, both of these mirrors must have some point over here, which is the midpoint of the mirror. This midpoint of the mirror is called as pole. So basically we are also defining one by one the terminologies related to our spherical mirrors. First one is the pole. Pole is nothing but the midpoint of our mirror part. Now, next one is center of curvature. Center of curvature is nothing but the center of the sphere of which our spherical mirror is a part. This is the center of curvature. So both these mirrors' center of curvature will be exactly the same because this mirror is also a part of this sphere. Our concave mirror is also a part of this sphere. Now, coming on to our next part, it is called as radius of curvature. So, radius of curvature, radius for any sphere or any circle, if you could just imagine this sphere as a circle in 2D view, radius of curvature would be nothing but the line or the distance or the length starting from center to any point on the mirror, right? If we just connect center of curvature with pole, either towards right hand side for our concave mirror, towards left hand side for our convex mirror, what do we have? We will have a straight line crossing our mirror. The straight line joining the center of curvature and pole of the mirror is known as our principal axis. Alright then. So, can we say that the distance between C and P is also our radius of curvature? Of course it is, because this distance is starting from point C and ending at point P, which is a point on the sphere or on the mirror. So this length is also called as radius of curvature. Now, coming on to our next point called as focus. So, focus in case of our concave mirror. If let's suppose this mirror is starting from here, this is nothing, this part, let's ignore this part. All the rays coming parallel to the principal axis after reflection, they pass by a common point, and this point is called focus point. So focus is the point where all the rays parallel to principal axis after striking our mirror goes or intersect at that point. Here, in case of our convex mirror, reflecting part is this, rays parallel to our principal axis would be coming like this. Now, here it will be a diverging mirror. If we just draw a normal at this point, of course that normal would pass through center of curvature. We are drawing the normal over here, we are drawing the normal over here and over here. At this normal, angle I equals to angle R, angle I equals to angle R, angle I equals to angle R, angle I equals to angle R. If we just reproduce it backward, all the reflecting rays, if we are to just reproduce it backward, we will get an imaginary focus in case of a convex mirror. This imaginary focus is also called as virtual focus. So, in case of concave mirror, we shall be getting a real focus because light rays are actually intersecting at this point. In case of convex mirror, we shall be getting a virtual focus because light rays appear to come from this point because they are actually diverging from the mirror. Okay. What about the focal length? Focal length is the distance between focus and pole. In this case also focal length is the distance between focus and pole. Mathematically, focal length is equal to R by 2. It is a simple geometry over here where we are taking approximation, and almost in all of the cases our focal length will come as half of our radius of curvature. So whenever there is a point given at focus, if somebody asks where shall be its center of curvature, you directly say it is at the distance of twice of focus from the pole. Alright, now let's come on to our 6 positions where we could see the image formation and the nature of the image in our spherical mirror. Let's start with concave mirror. The 6 positions shall be: first position at infinity, next position between infinity and C, which is known as beyond C, third position at C, fourth position between C and F, fifth position between at F, and sixth position would be between F and P. Let's see what those directions would look like. Let's come to the cases of image formation by concave mirror. But before that, we must know the rules behind the image formation through concave mirror. How our ray of light would come, where it would strike, and from which point it would go back. First rule. In case of our concave mirror, a ray of light coming parallel to the principal axis after reflection always pass through focus. Our second rule. A ray of light coming through the focus after striking our mirror will reflect back going parallel to our principal axis. Third rule. Any ray of light passing through the center of curvature striking the mirror will always retrace its path. Why? Because third case is the case of normal incidence. Through center of curvature, any line drawn on the mirror will act as normal, and upon normal incidence, our ray of light always reflect back in the same path. These are the cases for our concave mirror image formation. These are called as rules. Rules of image formation. Using any 2 rays out of the 3, we could easily define the nature and size of image as well as the position for different positions of the object using our ray diagram. Let's take it one by one. Let's suppose this is our concave mirror, this is pole, this is focus, this is center of curvature. For our object that is kept at position infinity, let's see how our image would come like, how our ray diagram would look like. An object kept at infinity would always give you parallel light rays. We are supposing the rays parallel to principal axis, so that after reflection, these rays pass through focus point. Alright, now here the point of actual intersection of our rays is what focus point. That means our image has been formed at focus. Nature of the image. Just see, the size of the object will always be counted taking our principal axis as the ground position or the mean position, as well as for the image. Here our rays are actually intersecting at the point on the principal axis. That means our image is real and inverted. Remember our acronym RIVER. Size of the image is highly diminished. Let's come on to our second position. Let's come to our second position where the object is kept between infinity and C, or the position that we call as beyond C. Here, if we just look over your ray diagram, the image is formed at some place between F and C, right? So here the image is formed between F and C. If you just compare the object and the image, you would see The image is formed by the actual intersection of the light rays and it is actually inverted. Hence, our nature of the image is real and inverted, while the size of the image with comparison to object is diminished. Diminished or smaller, you could use any word. Coming on to our third case where the object is kept at C. When the object is kept at point C, you could just see from the ray diagram that the image is also formed at C. When the object is at C, image is also formed at C. Nature of the image, since the image is formed by the actual intersection of our light rays, that means our image is for sure real. You could see if this is our object AB, then our image is A dash, B dash. Image is inverted with respect to the object. And here in this case, our image will be of same size. Let's come to our next position where the object is kept between C and F. For that position, let us see the ray diagram. Our next position where object is kept between C and F. From the ray diagram, it is easily understood that the image is formed beyond C. So, just as the object is moving towards the mirror, our image is moving away from the mirror. Now, our image is enlarged as compared to our object, but again it is real and inverted. So, when it is between C and F, image formed is beyond C. Our image is again real and inverted, but this time our image is enlarged. Same way we draw the cases when the object is at focus. In that case, our image will be formed at infinity. You could easily draw it using a scale and a pencil. So, when the object is at F, our image is formed at infinity. Again, the image is real and inverted, but this time, since it is formed at infinity, so it is highly enlarged. Let us look at the ray diagram for this case. In this case, we shall be using our important fourth law, which is not being used in above four cases but shall be really helpful in the fifth and sixth case, which is whenever a ray of light strikes the mirror at pole, it will go back in the same medium making the same angle. Why? Because from pole and CP forms a normal on the mirror, and any ray making some angle with the mirror after reflection forms the same angle. This is really helpful in our last case, that is where object is kept at focus and image is formed at infinity. Let us see how. Look over here for the fifth case. For the fifth case, our object is kept at focus. A ray parallel to principal axis passes from the focus after reflection. A ray striking the mirror at pole goes back in the same medium making the same angle as CP forms the normal, where we are using our fourth rule. Here you could see these two rays are almost parallel to each other, and any two rays, from the basic definition of parallel lines, any two rays parallel to each other will always meet at infinity only. That's why we say that our image is formed at infinity. And you could just see these two ray lines are going back in this direction. That is, they are going farther and farther away from our principal axis. Hence, the size of the image is highly enlarged. Let's talk about our last position, where now our object is further shifted towards the mirror between F and P. Now, in this case, let's see what would be the nature of the image and size as well as the position. Let us draw its ray diagram. Alright, for our sixth position where our object is between F and P, let's see a ray coming parallel to the principal axis would go through focus, right? But the object hinders its path. Okay, no problem. A ray passing through the pole will go back making the same angle. If we are to just draw it like this, these two rays will never intersect. These are the diverging rays on the front of the mirror. So to make the image, what we will do? We will just produce these rays backward. Producing these rays backward, we get a point of intersection behind the mirror where ray of light appear to diverge from, and so we have a virtual image of our real object. So in the last case, what we have? We have our image formed behind the mirror. In this case, it is virtual and erect. Also, if you could just compare the sizes of our object and image, the image is again enlarged. The sixth position, that is this position between F and P, is highly useful in day-to-day lives, such as the application of concave mirror forming an enlarged virtual image is being used as a shaving mirror or is being used by the dentist as their mirrors. Otherwise, the basic application of concave mirrors, such as the first one, where object is at infinity and image is formed at F. This application is being used in our TV antennas, right? Where our any TV antenna, let's say Dish TV or any Tata Sky disk, it takes the rays, our channel or radio waves, and it reflected at the point focus where we have got our receiver, and so we get really good signals and we see our channels. Other position of our concave mirror. Here concave mirror is making diminished or same size images. In these such cases, concave mirror are acting as converging mirrors. The application of converging mirrors are in the car headlights. Also their application are in the lighthouses and so all these things. Alright, let's come to our case where we'll see image formation using convex mirror. Rules of image formation in case of a convex mirror. A ray coming parallel to the principal axis after reflection will appear to come from focus point. A ray which is coming towards the focus point after striking our convex mirror will go parallel to the principal axis. Third one, a ray appear to be going towards C after reflection will again retrace its path and go back in the same direction. Fourth one, a ray of light striking at the pole after reflection forming the same angle will go back in the same media. When we talk about the image formation in case of convex mirror, we have got just two cases. Our first case is when our object is kept at infinity. From the definition of focus point, we will have its image formation such as like this. When the object is kept at infinity, the rays will be coming parallel to the principal axis, and after reflection, rays would go like this, which when further produced will appear to meet at this point. This is the first case. So here in this case, our image position is at F but behind the mirror. Nature of the image. Of course, since we have to produce it by ourselves, so nature of the image is virtual and erect, while size of the image is highly diminished. Now, talking about the next case, where when we keep our object anywhere between infinity and pole. Let's see how our image would look like. In the latter case, when the object is kept anywhere between infinity and pole, a ray going parallel would appear to come from focus. A ray striking the mirror at pole will go back in the same direction, making the same angle. When we produce both the rays backward, we find that both the rays intersect each other at somewhere between pole and focus. Here, in this case, the image formed is between pole and focus. Yes, again behind the mirror. Here also the image formed is virtual and erect. At the same time, the image is diminished. These are the two cases of convex mirrors based on which they have got their applications in things like rear view mirrors or security mirrors in the malls. You might have seen some metal balls in security malls. Those metal balls act as convex mirror. You might have seen the rear view mirror in your cars. Those rear view mirrors act as convex mirrors. Also, the application of convex mirrors are in your street lights, where you need to diverge out the rays coming. So, these are the image formation for your spherical mirrors. First, we have already discussed about concave. Now, we have discussed about convex. In the next lecture, we shall be proceeding with our mirror formula and magnification, and shall see some problems related to it.